In this video we're going to look and see how we fabricate our devices on silicon. We start off with a silicon ingot, and these range from 3 inches diameter all the way up to 12 inches in diameter. Once we've produced the ingot, we slice it into little discs, and these are the silicon wafers that you've possibly seen before. Each of them is approximately 1/8 of an inch thick, and they look almost like a music CD. Now, just to give you an indication of scale, I've got one of these ingots next to a person, and you can see this is about 6 or 7 feet long. In order to produce one of these ingots, we have a vat of molten silicon, and we drop in what is called a seed crystal, and the whole apparatus is rotated, and the seed crystal is drawn up the way, and as it is drawn up, the silicon comes with it and grows up and produces one of these ingots. Now obviously there's a lot more to it than the description I've given in the last 1 minute, but there's enough there for us just to get an indication of where our wafers come from. So now we have our silicon wafer, let's see how we can take these and we can produce our actual devices on these wafers. We're going to look at the changes that we can make to a silicon wafer, and we're going to split them into 3 broad categories. Category 1 are changes that we can make on top of the silicon wafer. The category number 2 are changes that we can make within the silicon wafer. So for example, creating N-type and P-type areas of dopant. Thirdly, we're going to look at processes that both grow on top of the silicon wafer and inside the silicon. So the first category we're going to look at is what we can do on top of the silicon wafer. And first of all, we're going to look at a process called lithography. Now, in order to ensure that we have only a particular region of the wafer available that is active to us, we need to have some way of defining set regions of the wafer. And we do that using photolithography, or what is shortened to here, lithography. So let's say, for example, we wanted to create a transistor and we wanted to put down 2 N-type materials in order to create the drain and the source. Then we have to have access to just those particular regions in order to add the dopant in to create the N-type and P-type materials. So we do this by first of all working through a process on the top of the layer here called deposition. So what we can do is we can deposit a polymer material called a resist, and this goes over the entire wafer. We then create something called a photoreticule, or it's shortened to a mask, and this is like the negative in a photograph. This photoresist is ultraviolet sensitive, that is sensitive to light. So what we can do is we can create a pattern on this mask. We can shine the light on this pattern, and whenever the light hits that here, it's going to act on this photoresist. Now the photoresist can be both a positive resist or a negative resist. So once we've added this, we can go through another process called etching. And what this does is it clears away, in this instance for a positive resist, it clears away the area that has had light shone in it, and it retains the area that is in shadow. So a negative resist would work in the opposite. It would maintain the resist in the area where the light is shone in it, and it would etch away the area that has been in shadow. So this is going to give us access to just this region here of the wafer. So this will allow us to then go ahead and add impurities to just this region. So that's if it was a positive resist. If it was a negative resist, we would have access to this area here and this area. So these areas would then become the active areas. So we've looked at 3 different processes here. Above the region, we're going to have our lithography, which entails a deposition of a resist and then the etching of that resist to create an active region. Now we don't just have to do this with a resist, we can add in different types of layers here. So for example, what we could do is, if we wanted to have an extra layer of pure silicon, so this is a layer that's the same as our substrate here, we could grow an epitaxial layer. So this epitaxial layer is just another layer of silicon that we'll have access to. And again, we can etch away certain regions of it, and we can add photoresist on top, and we can again do etching and other processes. So that's a broad introduction to the processes above the silicon layer. So let's have a look at the processes that we can do within the silicon. The process that we're interested in is doping. So let's say we have our silicon wafer here in blue. We can grow on top of it a resist. We could shine light through a photoreticule or mask, and if it's a positive resist, we would etch away the area that had light shining on it, and it will reveal to us this region here of the silicon, which would then be our active region. So that's the process above the layer. So now within the silicon layer, we can diffuse the silicon, or we can implant the silicon to create these N-type or P-type wells. So the process of diffusion or implantation are just 2 different methods of creating the well. In diffusion, we have a gaseous material which diffuses into the region. In implantation, we have ions which fire down through and are directed onto particular areas within this window or active region. Now we don't need to do just diffusion then implantation. There are other processes which implant the ions into the silicon, and then we have the silicon heated up and the ions then diffuse further into the silicon. So this is a mixture of both implantation and diffusion. The final category are changes that are made both above the silicon layer and within the silicon. Now an example of this is oxide growth, and we use this to grow the oxide just below the gate of our MOSFET. So what we can do is we can, now using these 3 broad categories, we can produce our MOSFET transistor. And here's an idealized drawing of the MOSFET transistor here. We have our green oxide layers here, so here, and also here below the gate. We have our metal layer on the top here, so this is our connection to the gate, and the metal can be either metal or a polysilicon, which again is just a conductor. And then we have our 2 regions here, our source and our drain, which are being created by our doping either the N or the P type to create our device. So that's an overall description of the processes involved. So let's go ahead in the next video and we'll actually build up a little gate using this process. So thank you for listening. I'll get you in the next video. Goodbye.